Hey everyone, and welcome back to AI Paper Podcast.
Glad to be here.
Today we're diving into a paper that's causing quite a stir. Is noise conditioning necessary for denoising generative models? It really challenges a fundamental assumption about diffusion models like DALL-E 2 and stable diffusion.
Yeah, this paper is super interesting because it looks at noise conditioning.
Okay.
You know that key technique where you feed the noise level into the model when you're training it?
Right.
We always thought this is absolutely essential, but this paper suggests it might not be.
Whoa, hold on. We're getting rid of noise conditioning. That seems crazy. Can you explain why this is such a big deal for those of us who aren't, knee-deep in diffusion models every day?
Yeah, sure. So imagine you're training a model to create images.
Okay.
In diffusion models, what we do is we gradually inject noise into like a clean image.
Right.
Until it basically becomes pure noise.
Got it.
And the model learns to reverse this process, going from noise to a crisp image.
Okay.
Noise conditioning is like giving the model a roadmap, telling it how much noise is present at each step.
I see.
So it knows how much to denoise.
So it's like telling it, okay, you're at 50% noise now, you're at 25% noise now, and so on.
Exactly. And this paper's saying maybe we don't need to give it those hints.
Really?
And the really wild thing is they found that a lot of these models actually do pretty well without noise conditioning.
Huh.
Some models, especially like flow-based ones, actually do better without it.
Wait, better. Okay, so we need to back up for a second before we jump into the how and the why. Can we give our listeners like a quick TLDR of the paper's main points? For those who are listening on the go.
Sure. So the main takeaway here is that noise conditioning might not be as crucial as we thought for diffusion models.
Okay.
A lot of the research is suggesting that a lot of these models actually perform surprisingly well even without it.
Okay.
And some even perform better like flow-based models.
Right.
The second thing is the researchers actually developed a new noise-unconditional model.
Okay.
They call it UEDM.
UEDM, got it.
And it actually achieves a really impressive FID score of 2.23 on Cepher 10.
Wow.
Which is right up there with some of the best conditional models.
Okay.
And lastly, this discovery could lead to some really cool new advancements in generative modeling.
Okay.
Potentially even a resurgence in, those classical energy-based models.
Whoa. Okay, so those are some big claims. Let's unpack those one by one. So first off, how did the researchers actually test these noise-unconditional models?
Yeah, so they took a variety of different models.
Okay.
Diffusion models like IDDPM, D-DEM, ADM, EDM.
Okay.
Flow-based models like flow matching. They even looked at consistency models.
Cool.
And they basically trained these on Cepher 10.
Okay.
Both with and without noise conditioning, just to see what would happen.
And what did happen? Did everything fall apart?
Surprisingly, no. A lot of these models actually handled it pretty well.
Wow.
They still produced decent images.
Really?
So take IDDPM, for example.
Okay.
With noise conditioning, it gets an FID score of 3.13.
Mm-hmm.
Without it, that score goes up to 5.51.
Okay.
So there's a difference there.
Yeah.
But the model's still creating recognizable images.
So no abstract art explosions.
Exactly.
That's pretty impressive. But how's that even possible? I mean, the paper has to offer some kind of explanation for this robustness, right?
They do, and it's really interesting. They basically argue that in natural images, the noise level is often kind of implicitly encoded already.
Okay.
It's kind of like blind image denoising,
Yeah.
where you're trying to get rid of noise without knowing exactly how much was added in the first place.
So you're saying that even if you don't know the exact noise level, you can kind of tell how noisy an image is just by looking at it.
Yeah, exactly. And these noise-unconditional models might be doing something similar, implicitly estimating the noise level just from the image itself.
Okay.
And what they found was that the distribution of noise levels given a noisy image is highly concentrated, meaning that even without being explicitly told, the model can make a pretty good guess about what that noise level is.
Okay.
And they even visualize this in Figure 3 in the paper.
Wow, this is like really making me rethink everything I thought I knew about diffusion models. But wait, you said there was one model that didn't handle this lack of noise conditioning well.
Right.
D-DEM. What happened there?
D-DEM is the outlier.
Okay.
Without noise conditioning, it completely falls apart.
Oh, no.
Its FID score jumps from 399 to a massive 4090.
A 40-point jump.
The generated images are not good.
Okay, so if most models are doing fine without noise conditioning, and some are even doing better, why is D-DEM falling apart so badly?
So the authors actually go into the theoretical reasons for this.
Okay.
And they actually develop something called an error bound that can predict how a model will behave without noise conditioning.
Wait, so we can predict how badly a model is going to mess up before we even train it?
Yeah, and you know what? This error bound predicted D-DEM failure.
Really?
And you can see this in Figure 4.
Oh, wow, that's incredible. How does that even work?
So this error bound is based on the model's formulation and some dataset statistics.
Okay.
It's a really powerful tool for understanding, why some models are more sensitive to this loss of noise conditioning than others.
So I guess the question is, why is DM so sensitive to not having that noise level information?
So it comes down to D-DEM's sampling process.
Okay.
It uses a deterministic ODE solver.
Right.
Which basically means that errors can accumulate over time without any chance for correction.
Okay.
Think of it like walking a tightrope.
Okay.
One wrong step and it's all over.
So D-DEM's got no safety net.
Pretty much. Without noise conditioning to guide it, D-DEM makes a bunch of wrong steps and things fall apart.
Interesting.
What's interesting is when they use a stochastic SDE sampler, which introduces randomness,
Okay.
D-DEM actually does okay without noise conditioning.
Huh.
That randomness kind of acts as a safety net, allowing for some error correction.
So a little bit of randomness can actually be a good thing. That's kind of counterintuitive.
It is.
Okay, so before we get too lost in the theoretical weeds here, let's bring it back to that new model you mentioned.
Right.
UEDM, the one that got that crazy good FID score without noise conditioning.
So UEDM stands for Noise-unconditional EDM.
Okay.
And it was specifically designed to thrive without noise conditioning.
Okay.
And they achieved an FID of 2.23 on CFART 10, which is practically neck and neck with EDM score of 1.99 with noise conditioning.
That's amazing. How do they do that? Do they have to reinvent the wheel or something?
Well, not completely. UEDM is built upon EDM.
Okay.
But they kind of cleverly modified the schedules.
Okay.
Those functions that control how noise is added and removed during training?
Right.
They tweaked those to make the model more robust without needing that noise level information.
So they gave it some training wheels to help it ride without noise conditioning.
Exactly.
That's really cool. But what about all the other models? Did they just focus on UEDM, or did they play around with different ways of handling noise conditioning?
They actually explored a bunch of different scenarios.
Okay.
Like using a separate network to predict the noise level both with and without supervision.
Okay.
And the interesting thing is all of these different scenarios perform very similarly.
So it's not just about removing noise conditioning completely, it's about finding the best way to use the noise information.
Yeah, and this finding really emphasizes that the key seems to be tapping into this inherent information about noise levels that's already present in the data.
Okay.
Now, I know we've been talking a lot about CFAR 10,
Right.
but I want to assure our listeners this isn't just limited to CFAR 10.
Okay, good.
They actually tested these ideas on ImageNet 32x32 and FFHQ 64x64 as well.
And did the results hold up?
The trends did hold up.
Interesting.
Flow-based models still saw those improvements without noise conditioning, and diffusion models mostly degraded gracefully. No catastrophic failures, except for, of course, D-DEM.
D-DEM. Always D-DEM.
Yeah.
So it seems like this noise unconditional thing is like a legitimate thing in the world of generative modeling, but I think we need to take a closer look at that error bound and all of that theoretical magic happening behind the scenes.
Yeah, let's do it.
Let's dive deep into the math in part 2.
Sounds good. We'll see you there.
See you there?
Welcome back, everyone.
All right, so let's dive into this theoretical stuff.
Yeah.
And try to understand why these noise unconditional models actually work. And hopefully we can keep it, clear for everyone.
Right.
Even those of us who hasn't opened a calculus textbook in a while.
No calculus needed.
Okay, good.
We'll keep it high level. So really what we're trying to understand here is what is the neural network actually learning in these denoising models?
Okay.
And remember, we're training it to predict, either the clean image or the noise. But there's a bit of a subtle point here. So for a given noisy image, right?
Okay.
Multiple combinations of a clean image and noise could actually lead to the same result.
Wait, so it's not just one clean image plus noise equals noisy image?
Yeah, it's a little more complicated than that. So imagine a noisy picture of a cat.
Okay.
That noise could have come from, a blurry photo of a fluffy Persian cat.
Okay.
Or it could be different noise layered onto a sharp picture of a sleek Siamese.
I see.
And both of those would result in the same final noisy image.
So the model has to figure out not just the cat, but also what kind of noise created that image.
Precisely.
Okay.
And that's where this idea of an effective regression target comes into play.
Effective regression target.
Yeah, so this target is essentially the average of all the possible clean image and noise combinations that could have made the noisy image we're looking at.
So the model's trying to hit like a moving target, basically.
It is. And, with noise conditioning, the model gets a better estimate of this target. But here's the surprising thing, even without it, the model is still aiming for that same target.
Huh.
just with a little bit less precision.
So the model has like some kind of inherent understanding of the noise without even being told?
Yeah, that's the idea. So the authors actually went in and they analyzed the error that's introduced by removing noise conditioning.
Okay.
And they found that it depends on two main things. One is how easily can the model kind of guess the noise level from the image itself?
Okay, that makes sense.
And two are the schedules that are used in the model.
Okay.
Remember, those control how the noise is added and removed?
Right, right.
So if the noise is predictable and the schedules are designed well,
Okay.
then the model is much more likely to handle this lack of explicit noise information.
And that's why DTM struggles so much.
Exactly. DTM schedules combined with its deterministic sampler make it super sensitive to any errors in guessing that noise level.
DTM just can't catch a break. What about these other models that were, more robust?
Yeah, so the paper found that models like IDDPM and EDM,
Okay.
they have a more concentrated distribution of noise levels, right? Which means it's easier for them to guess the noise level correctly, even without explicit conditioning.
Okay.
Plus, their schedules are a little more flexible, so they allow for some error correction during sampling.
So they have like built-in noise intuition and are more forgiving if they make small errors.
Exactly.
Okay, that's really cool. But what about flow-based models? You mentioned that those actually get even better without noise conditioning. Why is that?
Great question. So flow-based models work a little differently than diffusion models.
Okay.
Instead of gradually adding and removing noise, they learn to transform a simple distribution,
Okay.
like a Gaussian, into the complex distribution of our data, our images.
Got it.
It's kind of like learning a flow field that morphs one shape into another.
So instead of like blurring and unblurring, they're warping and morphing.
Exactly.
I like that.
And it turns out that this flow field doesn't actually have to rely on that noise level.
Really?
In fact, the paper suggests that forcing it to depend on noise could actually hinder performance.
Interesting.
So by removing noise conditioning, we free up these flow-based models to find a more natural and efficient way of transforming the data.
That's why we see that performance boost.
Yeah, and all of this leads to a really interesting question. What does this mean for the future of generative AI?
That is the question, isn't it? And you mentioned energy-based models earlier.
Yeah.
Are those connected to this whole noise-unconditional thing?
They are, and that connection could be huge. But I think we need to dedicate part 3 of this deep dive
Okay.
to really unpacking the potential of EBMs.
All right, part 3 it is. I can't wait to talk about that. We'll see you all there. Welcome back to the show, everyone. We're wrapping up our deep dive into noise-unconditional models, and now we're going to explore this really interesting connection to energy-based models.
Yeah, this connection could really change the way we think about generative AI.
But before we go any further, can we do like a quick recap on EBMs for those listeners who maybe aren't as familiar with them? What are they and why do they matter here?
Yeah, so imagine a landscape, right, with like peaks and valleys.
Okay.
The peaks, they represent these high energy states.
Okay.
And the valleys are like low energy
Sort of
states.
visualizing this.
And what an EBM does is it learns to create this energy landscape.
Okay.
So that the data we want to generate, like, let's say, images of cats, settles nicely into those low energy valleys.
So the model is like sculpting this terrain.
Yeah.
So the good data naturally flows to the lowest points.
Exactly. And then to generate new data, you start with a random point on that landscape.
Okay.
And you basically let it roll downhill, guided by that energy function, until it lands in one of those valleys, and boom, you have a new cat image.
So that makes sense. But how do EBMs connect to these noise conditional models that we've been talking about?
So traditional diffusion models,
Okay.
with their reliance on noise conditioning, don't really fit into that EBM framework very well.
Okay.
Noise conditioning is like having a separate energy landscape for every single noise level.
Right.
It's as if like the terrain is constantly shifting while you're trying to find those low points.
So it's like trying to play marbles on a waterbed.
Exactly.
You can never really sell on a good spot.
Perfect analogy. But noise-unconditional models, they learn a single energy function
Okay.
that doesn't depend on the noise level. And this makes them much more aligned with that classic EBM concept of like a static energy landscape.
So now the marbles can actually settle.
Exactly.
This alignment with EBMs sounds like it could lead to some really exciting possibilities.
Absolutely. EBMs have a lot of great properties.
Like what?
So one is they're incredibly flexible.
Okay.
You can use them to model all sorts of data, not just images.
Okay.
And they also have a strong theoretical foundation, which gives us a much deeper understanding of, how they work.
So are you saying this shift towards noise-unconditional models could lead to like an EBN revival?
That's the million-dollar question.
Okay.
That's what researchers are really trying to figure out right now.
Right.
There are still some challenges with EBMs.
Yeah, I bet. Like what?
like figuring out how to train them efficiently and how to sample from them effectively.
Okay.
But the potential is there. It's huge.
Well, it definitely sounds like we're on the edge of some really cool new developments in generative AI. But before we get too carried away, I think it's time for our final provocative thought for our listeners to ponder.
All right, so here's one. If noise-unconditional models are a stepping stone towards these more, EBM-like approaches, could we eventually see models that aren't just powerful but also deeply connected to the physics of the real world?
Whoa. Okay, so models that don't just mimic data but actually understand the underlying principles that govern it. That would be revolutionary.
It would, and who knows, maybe this research on noise-unconditional models is the key to unlocking that next level of generative AI, where models go beyond just mimicking and actually start to truly understand.
Well, on that note, I think we're going to wrap up this deep dive, but I really encourage everyone to go and check out this paper. It's a fascinating read full of really thought-provoking insights, and, maybe it'll change the way you think about generative AI. Thanks for joining us, everyone.
See you next time.